Metallic bonding. What is it? What does it occur between? What does it look like in diagrammatic form? Right, metallic bonding. Well, to be honest, it is not the hardest one to work out what it occurs between because it is metallic, which should give you the clue that it occurs between metals. We've talked about this before in previous videos. What makes a metal a metal? What makes a metal is that it has the tendency to lose electrons. Now, when it's paired up with a non-metal which has a tendency to gain electrons, that works perfectly well. The metal transfers its electrons, outer shell electrons, to the non-metal, and we have ionic bonding. When you just get non-metals together, as you've probably seen in a previous video, the tendency is for everything to gain. How can everything gain? Everything can gain by sharing. So the question lies here, metallic, metals, tendency to lose electrons. How can everything lose electrons whilst staying overall neutral? Well, I've always taught it like this. The metals pretty much cheat. What they do is they have their outer shell electron and they lose it. But it can't go all that far away, so it ends up being what we call delocalized. And as you'll see in the diagrams below when we draw them in, you end up with what we call a sea of delocalized electrons. These delocalized electrons are free to move in and out and through the structure. And because of that, this allows metals, for example, to conduct electricity, something we'll look at in more detail in another video. So, let's look at a couple of examples and then come back to the definition. So, lithium. Lithium is a group 1 metal and it has the electronic configuration of 2, 1. The lithium ion is formed when that one outer shell electron is transferred away, as in the case of ionic bonding, forming ions, or in this case, when that one outer shell electron is delocalized. So we end up with an electronic configuration of just 2. This is sometimes written as 2 in square brackets with a +1 outside. I'm just throwing that in so you see it. It's not actually that important in terms of learning. You won't see it very often. However, the +1 is important. The +1 is important because what we have is once we've delocalized those electrons, we have a load of +1 cations. So this is going to be a +1 cation, this is going to be a +1 cation, +1, etc., etc. So, what have we got here? Well, we have built ourselves a lattice of cations. We have built ourselves a lattice, that means a giant repeating structure. I've drawn it in 2D here, but it would be in 3 dimensions if you think about it, of cations. Now, if it was just cations, they'd all be positive and they'd all repel each other, so the whole thing would fly apart. Plus, we have those delocalized electrons to account for. So, because lithium is a +1 cation, we have a lattice of cations, and we have one delocalized electron per cation. So, if I just look at the first cation here, if I'm just looking at this one, there will be an electron that came from that cation. And it's delocalized, so I can put it in a random place. I'm going to put it here. E- equaling a delocalized electron. Of course, what I'm doing here is I'm writing a key. Might as well finish the key off. +1, what's that? That is a lithium plus cation. You can write lithium plus, probably better to write lithium +1. Now, have a quick think. How many more electrons do you think I'm going to have to put in on this diagram? Well, for this diagram, I have chosen to draw in 9 cations. People often ask, why is it 3 by 3? It's 3 by 3 because that's big enough to show what's going on, but small enough not to be a complete pain to draw. So, each cation has one delocalized electron that came from it. So there's one delocalized electron per cation. I have 9 cations. Therefore, I need 9 delocalized electrons. I've already drawn in 1. Let's draw in the rest. 1 is already in, 2, 3, up to 9. You can see that they are randomly distributed throughout the system. Okay, so what's happening here? Well, we have some positive species, that is the lattice of cations, and we have some negative species, that is the delocalized electrons. So we can look at our definition. The electrostatic force of attraction between the lattice of metal cations, those are the positive things, and the C of delocalized electrons. Those are the electrons that were in the outer shell of the metal atoms when they were atoms. They get delocalized when those metals form cations. Okay, so let's have a look at a different example, magnesium. Magnesium is going to have an electronic configuration of 2, 8, 2. We are therefore going to delocalize. We're going to delocalize 2 electrons per cation. So at this point, you've already seen an example for a group 1 metal, lithium. Let's see maybe if you can do the rest of this diagram for yourself. So pause the video if you're confident and see if you can work out the rest of this diagram. Remember to draw in yourself a little key and let's see how you go. So if you had your own go, hopefully your diagram is going to look a little like what we have in front of us. So instead of +1 cations like we have for the group 1 metal lithium, we're in group 2, so it's going to be +2 cations because we are going to delocalize these 2 electrons. 2 electrons are delocalized per cation. We'll come back to that in a sec. So +2s, again, my grid here is a 3 by 3, there's 9 cations. Why? Just because it's an easy diagram to draw. It's big enough that the examiner is going to give us marks for it, and it's not too big that it's going to take us way too long to draw. Anything smaller than this, some mark schemes have not allowed. They've wanted a minimum of a 3 by 3 grid. So let's have a quick look at my key. The +2 is the magnesium 2+ cation. Sometimes you'll see these drawn up as a circle with Mg +2 inside. That's not how I do it, but it can be done like that as long as the key is consistent with the diagram. The electrons that are delocalized electrons are drawn as E minuses again, and this time I have 18 of them. Now, if you have a look at that, it's random. It's not easy for the examiner to read. So quite often I will actually add to my key E minus delocalized electrons 2 per cation, and I'll add that to my key. So if I did accidentally draw one more or one less, I'm probably going to get away with it because the examiner is going to see that I know what I'm talking about, and I'm going to see the 2 per cation over there. So there we go. Metallic bonding. What does it occur between? Well, hopefully it should be relatively obvious it occurs between metals. Metals are metals because of their tendency to lose electrons, energetically favourable for them to lose electrons. How are we going to lose electrons? We are going to delocalize them. We allow them, or the metals effectively allow them, the outer shell electrons, to flow in and around and between the cations. And because we have those negatively charged delocalized electrons sitting in between the positively charged cations, the repulsions that are going to occur between the cations are overcome effectively by the attraction between the cations and the delocalized electrons, and it is that attraction that keeps the whole lattice together, and it is that attraction which is the definition effectively of metallic bond. Definition being the electrostatic force of attraction between the lattice of metal cations, those are the positive things, and the sea of delocalized electrons, those are the negative things. So as always with these, go away, make your own notes, do your own practice, make your own revision notes, draw your own diagrams so you get your head round metallic bonding.